Today we look at calculus without limits. It's called quantum calculus, it's called business calculus. It's a very simple version of calculus, but it's identical to the calculus we actually will do. So we will deduce some rules for this calculus, which will be exactly the rules which we have also for the standard calculus. And so we essentially anticipate the entire course, culminating in a theorem which is called the fundamental theorem of calculus. So first of all, the two important notions are the difference. Let me just make a picture to this. So we have a function, and a function like this, f of x, and so we have x and then x plus h. H is a constant, a positive constant, which we just fix throughout the whole lecture. Think about it as something small. The universe would take the Planck constant 10 to the minus 34, something very, very small. But what we have here is a function value at x, and then we have a function value at x plus h. And what we do is, when we look at this expression, we look at fx plus h minus f of x, which is this part here, which is the rise. And that's this part here. And then we divide by the run, which is h. So that's the lower part, that's this. So that's a slope. In traditional calculus courses, this is called the average rate of change, which already kind of uses the fact that it is really the average of the rate of change between these 2 points, x and x plus h. But we don't take any limit here, so this is a finite step. We take a step and we look how much we have gone up. The other thing here is a sum. So what we do is we have the function. Okay, we have the function here, and then we start at 0. We have at h, and then we have at 2h, 3h, and then we have n minus 1 h, which is maybe our point x. So what we do is we sum up values. F of 0 is here times h, that's actually an area, and then f of h times h is also an area. F of 2h times h is again an area. F3h, so and so on. We add up all these areas, and then with n minus 1, so we go here until n times h. So maybe think about n times h as equal to as our x value. And that will be the integral later on when we define Riemann sums and define the limit h goes to 0. But we don't take limits yet. What we do is we have just finite differences and finite sums. And let me just make a few examples. So that's the second part here. So the examples, that was part 1. I leave this here, but let's look at a few examples. So first of all, if f of x is constant, you can see if f of x is constant, then you have the constant minus the constant over h. That's 0. So this is, let me just write this d already as d over dx. That's just the rule which we, from Wednesday on, will always do. So we have d over dx of f is equal to 0. And no, maybe not. Maybe I keep the d because we don't take the limit h goes to 0, and we also don't deform yet things. So we have f of x is equal to mx plus b. So if you have that, we just plug it in here, then we get mx plus h plus b over h minus mx plus b, the whole thing over h. You see the mx goes away, the b goes away, and the only thing, the h cancels out, so this is equal to m. More interesting, and that's we will do that in class, and also in the homework you will do that again. If you take the exponential function, so these are all deformed functions here, depending on h. This is 1 plus actually ax. Just take ax here. So 1 plus ax, x to the h. So that's what we just write as e to the ax, right? That's exp of ax. So this is the exponential function. But in this finite situation with finite h, that's the function, that's the compound interest formula. And then you can see, and we will do that in class, and you do that in the homework, you can see that the d of e to the ax is actually just a times e to the ax. Very important. And we will also see that if we take x to the n, we define x to the n times x minus h times x minus 2h to the x minus n minus 1h. If we define this like that, then we have also dx to the n is n times x to the n minus 1. So also already in the homework today, you will not write this bracket here, but this is just an indication that we actually also, you will not write here the h here. So the h is always in the background, and it's a deformation of the algebra we know. Let me just show you in an example here. For example, if x squared, so that's x times x minus h, you have already computed that when you take dx squared. So that you take this function evaluated at x plus h, which is x plus h times x, minus the function itself, x times x minus h, and then you can factor out the x, and this is x times x plus h minus x minus h. So the x goes away, the h goes, this becomes a plus, so this is 2h, and so this is, and you have that divided by h, divided by h, the h goes also away, this is just 2x. So you see, kind of, that was in the case n equal to 2, we get just 2 times x. And we can do that for every n, and you will do that in the homework also, say for another n again, and in class we will do it. We will do the computation again. So you see, kind of, when we do the computations with this function, we get the rules, which you might already have seen in high school, differentiation rules. And in the limit h goes to 0, these are then the traditional function. By the way, the sine and cosine function you can get also from the exponential function by just taking a I with an imaginary I, and then you get the cosine and sine both, and all these rules which we have here you can just derive immediately from the definition. Fundamental theorem, we have two parts. The first part tells that if we take the difference of the sum, we get the function back. Let's just write this down. So first of all, we write the sum. So s of f of x, we have it there, that's just h, and then times f of 0 plus f of h plus f of 2h plus, and so on, f to the n minus 1 h. So that's the sum, which will later become integral. And then we have to also compute it in order to get the difference. We have also to evaluate it at x plus h. So when we take for x, this is our sum here, and so n of h is actually equal to x. So what we do is we go just to one step below x. So what we have here is f of 0. It's the same sum, but it goes a little bit further. Now if you take the difference between this, so we take this minus this, s of fx plus h minus s of fx, then you see that all these terms here actually are the same. So this cancels, this cancels, this cancels, everything cancels except the fn minus 1h is here, except the fnh here, which is fnh, which is f of x. So this is the this is the d of s of f of x. So that's the proof. That's the verification of this, and the picture is like that. So what we have is we have the function, and so we have up to n h, which is equal to x, and then we start at 0, right? We start at 0, and so this is h, and we go here 2h, here 3h, etc. Until n minus 1h, which is here. So this is every time we multiply by h, right? So we multiply by h every time. That's what we have here. We multiply by that h because that's the base, right? The base length is equal to h. And so what we have is we have all these sums, we sum it up, and all this area, these actually areas, they sum up like that. So that's what we have here. That's s of f of x. But if we take s of f of x plus h, what we get is the same thing, but we go one step further. So if we take that and make everything again, but with the same sum, but we have one step more. So we go until x plus h, not until x, right? When we take the difference, we go fx plus h, which means we take this sum up to x plus h, which means we stop here at nh. And you see kind of what happens is the blue one minus the green one is just this, it's just this part, and the h here cancels with that h here. So that's actually then just a function value here. This is then just f of x. So that's f of x here. So f of x times h, which appears here, and then if we take fx plus h minus f of x divided by h, then we get the same thing. So that's the picture, and that's already on this quantum or business calculus level. That's the proof of half of the fundamental theorem of calculus. Second part. The second part tells us that s of d of f of x is equal to f of x minus f of 0. Let's just write this down. First of all, we write dfx. So dfx, that's equal to f of x plus h minus f of x. So if we have d of f of kh, that's just f k plus 1h minus f kh. So what we have is actually when we take the sum of these differences, what we do is s of d of f of x. So let me just write it down. So what we have is we started at 0. So we have d of f of 0, which is just f of h minus f of 0 over h. And then the whole thing will be multiplied by h, right? Plus, and then we have f of 2h minus f of h over h, plus, let me just make it here with so that we have a little bit more space here. And then I have here 3h minus f2h plus etc., etc., and then plus f. And let's just see where this actually stops here. We have n minus 1, so we have nh minus f n minus 1 h over h. We just maybe add another point here, plus f n minus 2 n minus 1 h minus f n minus 2 h over h. Bracket closed. Now it's Candy Crush time. So what we have is fh over h. That appears here with a negative sign, right? So that candy goes away. And let's just see 2h here appears also with a negative sign. That Candy Crush goes away. And so on. We have everything is going away here. N minus 2 is going away with something before, and that goes away with that. So the only thing which is really surviving is the h cancels with the h, right? That we can cancel. So the only thing which is actually surviving here is the 0 part here, and the 0 part, and so the h actually goes away everywhere, right? So it's a 0 part and the last part here. So this is f of nh minus f of 0, which is just f of x minus 0. So that's this computation. And maybe also let's just make a little picture why this is actually working. What it means geometrically is what we have the function. Maybe at 0 it is here, maybe at x it's here. So that's the function. That's nh. And what we have done is we have looked at fh minus f0, which is this change here, going from here to here. So this change here plus this change, so this is h2h, plus this change, plus this change, plus this change, plus this change, etc. We look at all these changes here, like your bank account, and this is the income of what you buy, up and downs. You add them up. That's why it's called business calculus also. So what you do is you add up all these changes, and so the bank account value at x, at time x, minus the bank account value at 0, that's the sum of all these changes. So the first theorem tells us that d over dx, the integral from 0 to x, f of t dt, is just f of x. Nothing else than change of notation here. And the other thing is that if you integrate from 0 to x, d over dx, f of, just write t here, t dt. So then this is f of x minus f of 0. Now in the homework you will play around with examples, like let's do some computations. Let me just take one function. I take f is equal to 3 times e to the 5x plus sinus 17x plus maybe I take x to the 15 plus square root of x. So what we can do is we can differentiate and we can integrate. So when we differentiate, we use the rules here. We have the rules. So f d over dx of f of x. For the differentiation of the exponential, we get just the 5 down, 15e to the 5x. Here we get the 17 cosine 17x. Here we get 15x to the 14. And here when we take x equal to 1 half, n equal to 1/2, we get just 1/2 times 1 over the square root. We can also integrate. So when we integrate from 0 to x, f of t dt. So what happens when we integrate? We just reverse what we do when we differentiate. So we get 3/5 e to the 5x. Here we get the minus sign, cosine of 17x over 17. Here we get the x to the 16 over 16. And here we get the x to the 3/2 times 2/3. So this is the thing. But we also, with the rules, I actually want to make the rules here so that with the cosine. So I have actually, at x equal to 0, I want to get 0. So I actually have to take minus 3/5 and then plus 1 over 17. So at x equal to 0, this is all 0. Now at x equal to 0, I get a 0 area. So that's why the rules are taken like that. So these are the computations, and so this is a quantum business calculation, and it is exactly the same than the calculations we are going to do once we have taken the limits. When h goes to 0, this will be the derivative. When h goes to 0, this will be the integral. But for that, we have a couple of weeks until we really get to that.